This is problem number 23 on page 97. And it reads, 2 cosine x dy equals parentheses y sine x minus y cubed dx. And then there's the initial condition, y at 0 equal to 1. So now I suspect this may be a Bernoulli equation because of the y cubed term, a power higher than 1 of y. So I'm going to first of all take this from the differential form, which it is in, into the derivative form. And I'm going to choose to divide everything by dx. Now I could also do this by dividing everything by dy. I don't know if it's solvable that way, but I want to get dy dx, and principally my choice here is because the initial condition implies that we're treating x as the independent variable or input variable and y as the dependent or output variable. So y as a function of x, it would be natural to think about dy dx rather than dx dy. So hope that made sense. Anyway, let's see what we get here. And so dividing here, we'll get 2 cosine of x y prime equals, and here are the cancels, so y sine x minus y cubed. Now I'm going to bring this over to this side. So 2 cosine of x y prime minus y sine x equals negative y cubed. And let's divide by 2 cosine x, and I think you'll see why here in a moment, why we're doing all this. So this gives us just plain old y prime minus, and I have a 1/2 minus 1/2. Sine over cosine is tangent, so tangent x times y equals to, over here I've got minus 1/2, and then 1 over cosine is the secant function, so let's write it as secant x times y cubed. So, is that a bona fide Bernoulli equation? Well, indeed it is, because the Bernoulli form is y prime plus p of x times y equal to q of x times y to the nth power. And we see here that p of x is this mess right here times y. Q of x is the minus 1/2 secant x times y to the 3rd power. So n is equal to 3 here. And the technique that Bernoulli figured out was to take this equation and multiply it by 1 minus n y to the negative n power. So in this case that would be 1 minus 3 is negative 2 y to the negative 3rd power. Alright, so let me erase this stuff here and multiply by this factor. So I took minus 2 y to the negative 3rd power, multiplied that equation I had, and when I multiply it through, I have minus 2y to the negative 3rd times y prime. The negative cancels, the 2 cancels, so I have tangent x times y to the negative 2nd, because I have y to the 1st times y to the negative 3rd. And then over here, the negative and the 2 cancels, leaving just secant x, and of course the y's cancel. So we're down to this form right here, and to make it look familiar, I'm going to change my variable here, change the y variables out, because I think I want this to be u. So let's let, and I'm going to separate this off here, I'm going to let u equal to y to the minus 2 power, and then u prime, take the derivative of this equation with respect to x, and we'll get negative 2 y to the negative 3rd power times y prime, which is what I have here, isn't it? So here is u prime plus tangent x times u equals secant x. So let me write that down here. This is, what did I say? U prime plus tangent x times u equals secant x. There we go. So there's my equation in this new variable u after this adjustment. And now it looks like the type of equation that lends itself to the integrating factor technique we've been exploring. And where my integrating factor will be e to the tangent x power, integral of tangent x power. So I'm going to do some erasing. I'll transfer this up here and then we'll start working from there. I took the last equation I had and wrote it up here. So we have u prime plus tangent x times u equals secant x. And that's in the form for the integrating factor that I want to use. The integrating factor is e to the integral of this coefficient here, tangent x dx. And what's the integral of tangent x? Well, I looked it up. I don't have all these in my head so well, and but the integral of tangent x is minus natural log of the cosine of x. And here we can think of the minus sign as a negative 1 power, like so. That makes it convenient because being inverse functions, e and natural log will cancel in this case. So I get cosine x raised to the minus 1 power. Now that's not the inverse cosine function. This is the power of negative 1 applied to cosine x, so that makes it a reciprocal of cosine. 1 over cosine, which is secant. So my integrating factor is the secant function. And now I'm going to take this equation, multiply by secant of x, and that gives us u prime secant x plus tangent x secant x times u equals to secant squared x. Now, can we simplify this? Well, tangent's sine over cosine, secant's 1 over cosine, so this product is sine over cosine squared. That's pretty awkward, so I'm going to just leave it tangent secant. And the idea, again, with these integrating factors is when we multiply here, it turns the left side into the derivative of the integrating factor times our dependent variable, in this case u. And over here I still have secant squared x. So let's just double check that. If I take this derivative, we have a product rule, so I have u prime times secant x plus derivative of secant is secant times tangent, and then times u. So all that works out. And if we bring the dx over by multiplication, I have the derivative of secant x times u equal to secant squared x dx. Alright, well, at that point we can integrate because we've separated the variables, we've separated the differentials. You might say, well, we didn't separate the variables, I have x and u here. Well, in a sense, we're thinking of this parentheses as its own variable. Okay, the derivative of this variable, I'm sorry, the integral of the differential of that variable is simply the variable. So this gives me secant x times u equals, now you might recall that the derivative of the tangent function is secant squared. So if I integrate secant squared, I get tangent. So that's tangent x plus the constant. Alright, so we're down to secant x times u equals tangent x plus a constant. And I think at this point I'm wanting to go ahead and put in the initial conditions. So let me do some erasing here so we have some room to work. Now this is where we left off. We had secant x times u equals tangent x plus c. And recall that our initial condition, I'll write out here, was y at 0 equal to 1. Well, if that means that when x equals to 0, then y equals to 1. Well, when y equals to 1, 1 to the negative 2 power is still 1. That means u equals to 1. So I don't have to necessarily put it back in terms of x and y yet in order to apply the initial conditions. I can just figure out what u would be with the initial condition. So if I plug this in, u equals to 1 times secant is 0, so I have secant 0 times 1 equals tangent 0 plus a constant. Well, secant is 1 over cosine. Cosine is 0 is 1, so secant of 0 is 1 over 1. 1 times 1 is equal to tangent of 0 is 0 plus c. So that means my additive constant is 1. All right, well, so I'm going to go ahead and replace the c up here with a 1. And now let's go ahead and replace the u with y to the negative 2 power. So I end up with y to the negative 2 times secant x equals tangent x plus 1. And if we multiply by y squared, because y to the minus 2 is kind of on the ugly side, isn't it? So we get our positive integer powers. So that will cancel the y to the negative 2 here. So secant x equals to y squared times tangent x plus 1. And I think that's the book answer. I sure hope it is. Moment of truth. Secant x equals to y squared parentheses tangent x plus 1. We got it. So, all right. Well, that's some examples there on integrating factors and Bernoulli equations. So we're done with chapter 2, and let's go on to chapter 3, which is applying some of these equations.